Everyone, this is an audio recording for visually impaired student. Today I am going to read a chapter from Pradeep Physical Chemistry written by Dr. S.C. Khetrapal. Chapter name Thermodynamics Second. Introduction. Need for the second law and the different statement of the law. The first law of thermodynamics had certain serious limitation. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequences, some definition given to the second law are briefly given below. First, a major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of the energy involved, but it provides no longer information concerning the feasibility of the process. Example, whether the process is possible or not. For example, the first law does not indicate whether the heat can flow from cold end to the hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the another end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supply answer to the above question by starting that all spontaneous process like the flow of heat from hot end to the cold end, diffusion of gas from high to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that the term spontaneous does not give an idea of the rate of the process. Example, whether the process take place fast or slowly, all that it implies that is that a process can occur without the help of any external agency. Second, the first law states that when a heat is converted into the work obtained is equivalent to the heat absorbed. However, it had been seen from experience that the heat absorbed cannot be completely converted into the work without leaving some changes in the system or the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as below. The complete conversion of heat into the work is impossible without leaving some effect elsewhere. Second definition. Beside the above definition, a number of other definition has been given to the second law of thermodynamics. The important are first, it is impossible to construct a machine functioning in cycle which can convert heat completely into the equivalent amount of work without producing some changes else. Third definition. Without the use of any external agency, the heat cannot by itself passes from a colder to the hotter body. For definition, the term functioning in cycle is introduced in a above definition to indicate that a machine must return to its original state at regular interval so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, del U is equal to 0, so that Q is equal to W. Example, the work done is exactly equal to the heat absorbed by the system. In the other word, in this process, heat is completely converted into the work. However, it is important to observe that this convention is accompanied by an increase in the volume of the gas so that the system has undergo a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding section of this chapter. Fraction of the heat absorbed by a machine that it can be transferred into the work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by N is equal to W by Q. The machine used for the conversion of heat into the work is called the heat engine. In order to bring about this conversion, the energy absorbed heat from a heat reservoir at a high temperature called a source and convert a part of it into the work and return the remainder to the heat reservoir at a low temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sadi Carnot devised a technique called the Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducting in this manner is called the cyclic process. The engine chosen by Carnot, called Carnot engine, for the purpose of the calculation of the efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless frictionless piston so that all the operation in the cyclic are carried out reversibly. For this reason, it was called the reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can be flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a high temperature T2 source and the other at a low temperature T1 called the sink. If some operation is carried out by placing the cylinder in the source or a sink, it can change heat with it and hence the temperature remain constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surrounding, and hence the process is a adiabatically process. The Carnot cycle consists of the four different operations which can be represented on a pressure volume diagram, sometimes called an indicator diagram, shown in figure 2.1. These operations are carried out as shown in figure 2.2 and are briefly described below. Isothermal expansion. The cylinder contains 1 mole of ideal gas occupying a volume V1 is placed in contact with the source heat reservoir at temperature T2. The gas absorbed the heat Q2 from the source and expand isothermally and reversibility its volume has to increase to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done W1 by the 1 mole of ideal gas will be given by minus W1 is equal to RT2 ln V2 upon V1. Further, for an ideal gas, the work done is equal to the heat absorbed Q2, so that minus W1 is equal to Q2 is equal to RT2 ln V2 upon V1. Here W1 has been taken as negative and Q2 as a positive by the latest SI convention of the sign. Second, adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulated material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enter or leave the system, the temperature must fall. The reversible adiabatic expansions continue till the temperature had to fallen to T1, which is the temperature of the sink. Suppose the corresponding volume become V3 and the path is shown by the adiabatic curve is BC. The work done W2 is given by minus W2 is equal to CV. T1 minus T2 is equal to minus CV T2 minus T1, where CV is the heat capacity of the ideal gas. Again, W2 is negative by the usual convention of the sign. Third, isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink, the heat reservoir at a low temperature T1. The gas is compressed isothermal and reversible till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken by the positive by the usual convention of the sign and an hence would be given by W3 is equal to RT1 ln V4 by V3. During the operation, an amount of heat Q1 exactly equal to Q3, W3 will be returned to the sink at T1. For example, heat has been given out by the system. Using the appropriate convention of the sign, Q1 will be negative and W3 will be positive. So that minus Q1 is equal to W is equal to RT1 ln V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2 and the work done is positive by the convention of sign and will be given by W4 is equal to CV T2 minus T1. As a result of these four conventions, the system has returned to its original state so that a reversible cycle has been completed. The net work done by the system will be given W is equal to minus W1 plus negative of minus W2 plus W3 plus W4. RT2 ln V2 upon V1 minus CV T2 minus T1 plus RT1 ln V4 by V3 plus CV T2 minus T1. From there we have RT2 ln V2 upon V1 plus RT1 ln V4 upon V3. Since V1 and V4 lie on an adiabatic curve and V3 and V2 lie on another, it follows that V4 upon V1 power gamma minus 1 is equal to T2 minus T1 and T2 minus T1 T2 divided by T1 is equal to V3 upon V2 की power gamma minus 1. Comparing this equation 9 and 10, then we get V4 by V1 is equal to V3 upon V2 or V4 upon V3 is equal to V1 upon V2. Putting this value in equation, we get RT2 ln V2 upon V1 plus RT1 ln V1 upon V2 and RT2 ln V2 upon V1 minus RT1 ln V2 upon V1. So R taken common, R T2 minus T1 ln V2 upon V1. Dividing this equation, so we get W by Q2 is equal to T2 minus T1 upon T2, which give the efficiency of the Carnot cycle or engine. Carnot theorem. From equation 13, it is clear that the efficiency of the reversible heat engine depend only upon the temperature of the source and the sink and is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation because the work done in the adiabatic operation second and fourth cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum, whereas the work done on the gases during the reversible isothermal compression from C to D is minimum. And hence the total work done by the system, for example, the reversible heat engine or the Carnot engine is maximum for the specified condition and therefore the efficiency is maximum. The result that follow from the Carnot cycle is called a Carnot theorem. It may be stated as follows. The efficiency of a reversible heat engine depend upon the temperature of the source and the sink but doesn't depend upon the nature of the working substance. In other words, or reversible heat engine working between the same two temperatures have the same efficiency. Further, it states that the efficiency of reversible engine is maximum for the given temperature. And hence the quantity T2 minus T1 upon T2 is always less than unity. The efficiency of the heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follows. The heat engine absorbs a certain amount of heat from the source, convert a part of it into the work, and return the rest to the sink. In other words, it is impossible to convert heat completely into the work. Further combining equation, we get W is equal to Q1, Q2 minus Q1. The net work done by the system is equal to the net heat absorbed by the system. Putting the value of W in this, we get Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. And hence the efficiency of a heat engine may be given by any one of the following expansion. Eta is equal to W by Q2 is equal to Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. This result deviated for a reversible Carnot cycle leads to the introduction of the new thermodynamic term called entropy as discussed in section 2.5. Thermodynamic scale of temperature. From our earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of the capillary tube and marking 0 when it is placed in contact with ice and making 100 when it is placed in the boiling water. The length between the 2 points is then divided into 100 equal part called the degree. The scale of temperature thus obtained called the Celsius scale of temperature. However, because different liquid expand to different extent, their coefficient of expansion are different and also they do not expand uniformly over a given range. Thermometer constructed by using different liquid will show different numerical value of temperature between their fixed point. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer, but may show 28.8 degrees Celsius with any alcohol thermometer. The problem was solved by the study of property of gases. It was found that an ideal gas or a perfect gas ceased to exist at temperature at minus 273.15 degrees Celsius. This temperature was called the 0 degree absolute. The scale developed on this basis is called the perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was first to develop a scale of temperature that was independent on the nature of any gas taken in a heat engine. The scale of temperature is called a thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly discussed below. Suppose there are the two constant temperature, heat reservoir, one acting as a source and other acting as a sink, and a reversible heat engine operate between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from source and the heat lost to the sink. If Q2 is the heat transfer from the source, मतलब heat reservoir at high temperature, and Q1 is the heat transfer in a sink reservoir at low temperature, then if their temperature on the thermodynamic or Kelvin scale was represented by theta 2 and theta 1 respectively, we have Q2 upon Q1 is equal to theta 2 by theta 1. Then the ratio of the two temperature has been defined in a manner independent of the nature of the thermodynamic substance. Taking the reciprocal of the both side and subtracting the result from unity, we get 1 minus q1 upon q2 is equal to 1 minus theta 1 by theta 2. q2 minus q1 upon q2 is equal to theta 2 minus theta 1 upon theta 2. Putting theta 1 is equal to 0. 0 of the new scale we get q2 minus q1 upon q2 is equal to 1. This implies that the 0 on the Kelvin scale is the temperature of the sink for the reversible heat engine, where efficiency is unity. For example, which is capable of converting heat completely into the work. It may be seen that it is possible only at absolute zero on the ideal gas scale of temperature. This leads to the conclusion that Kelvin scale or a gas scale are identical, provided the gas is ideal. The temperature on thermodynamic scale are therefore expressed in a term of the degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equal to that of the triple point of water, 273.16 Kelvin, then Kelvin is exactly equal to the Celsius degree. For this reason, the temperature on the absolute scale in which the melting point of an ice is taken as 273.16 is often referred to as degrees Kelvin. It may be concluded that thermodynamic scale of temperature is defined on the basis of the second law of thermodynamics is more basic than that based on the ideal gas because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of entropy as a state function. For a reversible Carnot cycle working between temperature T2 and T1, it has been seen that Q2 minus Q1 upon Q2 is equal to T2 minus T1 by T2, where Q2 is the heat absorbed isothermally and reversibly at temperature T2, and Q1 is the heat lost isothermal and reversibly at temperature T1. The above equation may be simplified as 1 minus q1 upon q2 is equal to 1 minus t1 upon t2, or q2 upon t2 is equal to q1 upon t1. Q by t is equal to constant. Thus, we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost in is a constant quantity for a particular system. Further in equation, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at the temperature T1. If Q were the heat absorbed at temperature T1, then the equation becomes Q2 upon T2 is equal to minus Q1 upon T1, or Q2 upon T2 plus Q1 upon T1 is equal to 0. Summation of Q by T is equal to 0. Now consider any reversible cycle ABA. It may be regarded as been made by a number of Carnot cycles drawn across the diagram, starting from A and goes through all the cycles successively from A to B. It can be shown that all the paths inside the closed curve ABA cancel each other, leaving on the zigzag path, which is almost the same as the path ABA of the reversible cycle. By making each Carnot cycle smaller and increase their number, it can be made to corresponding more closely to ABA. The reversible cycle can therefore be regarded as being made up of the infinite number of Carnot cycles. For example, each of these cycles we have summation of q by t is equal to 0. Hence, for the infinite number of Carnot cycle, del q by t is equal to 0, where del q is very small quantity of the heat absorbed at temperature T during the small isothermal change of the reversible process. Further, the above term may be divided into the two parts, one for the path A to B and other for the back from B to A. This equation summation del q by t is equal to summation A tends to B del q by del t plus summation B tends to A del q by t is equal to 0. Or we have to write summation A tends to B del q by t is equal to negative of summation B tends to A del q by t, or q by t A tends to B is equal to minus of q by t B tends to A. This implies that total value of quantity q by t for the path A to B is equal to the total value of the quantity q by t for the reverse path B to A. Hence, it may be concluded that the quantity q by t is a state function. Its value depend only upon the initial state and the final state and independent upon the path. Obviously, q by t is the change in the value of a quantity or a function having some definite values at a and b depending upon the value of pressure, temperature and volume. This quantity or the function is called the entropy and is usually represented by the symbol S. Thus, if SA is the value of entropy at A and SP is the value at B, then we must have Q by T is equal to SB minus SA is equal to del S, where del S represents the total change in entropy is going from the initial state A to final state B. And hence, entropy can be defined as a state function, the change in the value of which from the initial state to the final state is equal to the quantity Q by T, the total heat absorbed reversibly and isothermally in going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. From equation, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that As entropy is a state function, therefore the value of entropy changes during the cycle should be depend upon the path. Whether the heat is absorbed reversibly or irreversibly during the process, and hence, since the derivation of the above result is based upon the Carnot cycle in which the heat is absorbed reversibly. Therefore, the expansion for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol Q reversible in place of Q. The expansion may be written as del S is equal to Q reversible by temperature. For the entropy is a state function, a small change in its value can be expressed by ds, and it can be written ds is equal to Q reversible by temperature. Unit of entropy. From the expansion ds is equal to Q by T, it is obvious that the unit of entropy will be in calorie per degree if it is expressed in calorie. Further, the entropy is an extensive property. It is therefore important to mention the quantity of a substance involved. It is loosely expressed for 1 mole of the substance, and hence the entropy units are calorie per degree per mole. If it is measured in joule, the unit of entropy will be joule per degree per mole. Entropy change in a reversible process. Suppose a process occur under completely reversible condition. The heat is absorbed by the system reversibly and the heat is lost by the surrounding also reversibly. If Q reversible is the heat absorbed by the system, then the heat lost by the system is also very reversibly. If the process taken isothermally at absolute temperature T, then entropy changed by the system will be given by del S system is equal to Q reversible by T. And second, entropy change by the surrounding will be del S surrounding is equal to minus Q reversible by T. And hence the total entropy for the combined system and the surrounding will be del S system plus del S surrounding is equal to Q reversible by T minus Q reversible by T is equal to 0. Thus we conclude that in reversible process the net entropy for the combined system and the surrounding is 0. So there is no net change in entropy. Entropy change in a irreversible process. If any part of the process is irreversible, the process as a whole is irreversible. Suppose that the heat lost by the surrounding is Q irreversible. This heat will be absorbed by the system, but the entropy change of the system does not depend upon the heat actually absorbed, but it is depend upon the heat absorbed reversibly on the quantity Q reversible. If the heat is absorbed isothermally by the system at absolute temperature T, the entropy of the system will be del S system is equal to Q reversible by temperature. Further, suppose that the loss of the heat Q reversible by the surrounding take place infinitely slowly and the isothermal at the temperature T. Then the entropy change of the surrounding will be given by del S surrounding is equal to minus Q irreversible by T. The total entropy change for the combined system and the surrounding will therefore be del S of system plus del S of surrounding is equal to Q reversible by T minus Q irreversible by T. Now we know that the work done in a reversible process is a maximum work. Q reversible is greater than Q irreversible. Further, as a internal energy U is a state function, the value of del U is same whether the process is carried out reversible or irreversible. Del U is equal to Q reversible minus Q irreversible. Q reversible minus W reversible is equal to Q irreversible minus W irreversible. Combining this result, Q reversible is greater than Q irreversible. So Q irreversible by T is less than Q reversible by T. Q reversible by T minus Q irreversible by T is greater than 0. Combining this result can with the result given in equation third, we observe that del S of system plus del S of surrounding is greater than 0. Thus, it may be concluded that in any irreversible process, the entropy change for the combined system and the surrounding is greater than 0. An irreversible process is accompanied by the net increase of entropy. Since all spontaneous processes are thermodynamically irreversible, first definition of the second law of thermodynamics, it may be stated that all spontaneous processes are accompanied by a net increase of entropy. This is also one of the very common statement of the second law of thermodynamics. The result for the entropy change in a reversible process and that in an irreversible process may be combined together and put in the form del S of system plus del S of surrounding is greater than equal to 0, where the sign equal to stand for the reversible process and the sign greater than stand for the irreversible process. The exact calculation of the total entropy change during an irreversible process when the heat is flow from a body B at high temperature T2 to a body at temperature T1. When brought in contact with it, it may be carried out as follows. Suppose the heat lost by the body B is represented as Q irreversible. The flow of heat may be allowed to take place infinitely slowly so that it is absorbed by the body A, reversible and isothermally at temperature T1, which may be represented as Q reversible. The entropy change of the body B will be depend only on the Q reversible, and hence the entropy change of the body B is equal to negative of Q reversible by T2. Entropy change of body A is equal to positive of Q reversible by T1. Minus sign indicate decrease in entropy, while positive sign indicate the increase in entropy. So delta S is equal to Q reversible bracket start 1 by T1 minus 1 by T2 bracket close. Clausius inequality. As discussed below, for an irreversible process, the result given in equation 9 may be written as delta S of system plus delta S of surrounding is greater than 0. So delta S of surrounding is greater than negative of delta S of surrounding. So we have delta S of surrounding is equal to minus Q by T. Putting this equation, we get delta S of surrounding is greater than Q by T. For the small change, the above equation may be written as delta S of system is greater than minus delta S of surrounding. Delta S of system is greater than dq by t, and that are called the Clausius inequality. These equations show that irreversible processes are accompanied by increase of entropy. There is further illustrated with the help of the following two examples of irreversible process. Spontaneous expansion. A irreversible adiabatic expansion. Suppose the system undergo irreversible adiabatic change. Then dq is equal to 0 and hence by Clausius inequality ds of system is greater than 0. The entropy of the system has increased further as dq is equal to 0. This means that no heat is transferred into the surrounding, thus ds surrounding is equal to 0. And as the total entropy change, ds total is equal to ds system plus ds surrounding is equal to ds of system. But ds system is greater than 0 and hence ds of total is greater than 0. B irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant. Du is equal to 0 and hence according to the first law of thermodynamics, du is equal to dq plus dw. dq plus dw is equal to 0 or dq is equal to negative of dw. If the gas expands freely into vacuum, no work is done, so that dw is equal to 0. Substituting in equation give dq is equal to 0 and hence by Clausius inequality ds of system is greater than 0. Further, as dq is equal to 0, this implies that del S surrounding is equal to 0 and as the total entropy change as in the above cases, del S total is greater than 0. Second is spontaneous cooling. Suppose heat is transferred from one system at a high temperature T2 called the source and to another system to the low temperature T1 called the sink. If heat dq leave the source and enter the sink, entropy change of the source is equal to minus del q by T2 and entropy change of the sink is equal to plus dq by T1. The total entropy change ds total is equal to dq by T1 minus dq by T2 is equal to dq 1 by T1 minus 1 by T2. As T2 greater than T1, ds total is equal to positive. Example, cooling transfer of heat from hot body to cold body is accompanied by the increase of entropy. entropy change of the universe. Since all spontaneous processes occurring in nature are thermodynamically irreversible, these are accompanied by increase of entropy, and hence it may be concluded that entropy of a universe is continuously increases. This result is sometimes taken as another statement of the second law of thermodynamics. Thus, the main idea of the first and the second law of thermodynamics may be summoned in the following statement: the energy of universe is constant, whereas the entropy of a universe is continuously increased and tends to maximum. Entropy change for an ideal gas with change in P, V and T. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. If an infinitely small amount of heat dq reversible is supplied to the system reversibly and isothermally at the temperature T, then the entropy change accompanying the process will be given by ds is equal to dq reversible by temperature, according to the first law of thermodynamics for an infinitely process. Del Q is equal to del U minus del W. If the process is carried out reversibly, the equation second may be written as del Q reversible is equal to del U minus del W. Further, if the work is restricted to the work of expansion, as is usual the case for the process considering in chemical thermodynamic, then minus del of W is equal to PdV, where dV is the small increase in volume and P is the pressure of the system, which is very nearly equal to the external pressure because the process is carried out reversibly. Putting the value of del Q, del W from equation 4th in equation 3rd, we get del Q reversible is equal to del U plus PdV. Consider equation 5th. Substituting this equation in equation 1st, we get del S is equal to del U plus PdV by T. It may be written as TdS is equal to du plus PdV. Consider equation 6th. Now for 1 mole of an ideal gas, we know that Cv is equal to du upon dt. So du is equal to Cv upon dt. Consider equation 7, where Cv is the molar heat capacity at constant volume and Pv is equal to RT. So P is equal to RT by volume, where volume is the V is the volume of the system at temperature T and pressure P and R is the gas constant. Putting the value du and P from equation 7, 8 in equation 6, we get TdS is equal to Cv dt plus RT by V dV. So TdS is equal to ds is equal to Cv dt by T plus RdV by V. Consider equation 9. If the volume changes from V1 to V2, when the temperature changes from T1 to T2, then the entropy change accompanying the complete process will be given by ds limit S1 to S2 is equal to Cv dt upon T limit T1 to T2 plus R limit V1 to V2 dV upon V. Consider equation 10. Assuming that Cv remain constant in the temperature ranges T1 to T2, equation 10 may be written as del S is equal to Cv ln T2 upon T1 plus R ln V2 upon V1. Consider equation 11. This is an expression for the calculation of entropy changes of the 1 mole of an ideal gas, accompanying a process when temperature changes from T1 to T2. Thus, the volume changes from V1 to V2. Further, for 1 mole of an ideal gas may be written P1 V1 is equal to RT1 for the initial state. Consider equation 12. P2 V2 is equal to RT2 for the final state. Consider equation 13. Dividing equation 13 by equation 12, we get P2 V2 upon P1 V1 is equal to T2 upon T1. So V2 by V1 is equal to T2 by T1, P1 by P2. Putting this value in equation 11, we get del S is equal to Cv ln T2 upon T1 plus R ln T2 P1 by T1 P2. So we know that Cp minus Cv is equal to R. So Cv is equal to Cp minus R. Putting this equation in 15, we get Delta S is equal to Cp ln T2 upon T1 minus R ln T2 upon T1 plus L R ln T2 upon T1 plus R ln P1 upon P2. Delta S is equal to Cp ln T2 upon T1 plus R ln P1 upon P2. Consider equation 16. This is an expression for the calculation of the entropy changes of the 1 mole of an ideal gas, accompanying a process when temperature changes from T1 to T2 and the process changes from P1 to P2. Entropy change of an ideal gas in different process. Equation 11 gives us the entropy changes for 1 mole of an ideal gas when the temperature and volume are variable. Similarly, equation 16 gives the entropy change of 1 mole of an ideal gas when the temperature and pressure are variable. These equations are modified if conditions of constant temperature, pressure or volume are imposed. For example, first, if temperature is kept constant for isothermal process, T1 is equal to T2. Equation 11 and 16 are reduced to delta S is equal to R ln V2 upon V1 is equal to R ln P1 upon P2. Consider equation 17. Alternatively, this expression can be derived directly as follow. Del S is equal to Q reversible by temperature minus W maximum is equal to Q reversible is equal to nRT ln V2 upon V1. Consider equation 19. nRT ln P1 upon P2 is considered equation 20. Substituting the equation Q reversible from equation 19, 20 in equation 18, putting N is equal to 1 for 1 mole of an ideal gas, we get the result given in equation 17. Second, if the pressure is kept constant for isobaric process, the equation 16 can be modified to del S is equal to Cp ln T2 upon T1. Third, if volume is kept constant for isochoric process, V1 is equal to V2. The equation 11 will be reduced to delta S is equal to Cv ln T2 upon T1. Note carefully that all the expression derived above for the calculation of entropy change, del S involve the natural logarithm. Since logarithm table commonly used r to the base 10 in applying this formula, in x has to be first replaced by 2.303 log x, where x is the quantity like T2 upon T1, V2 upon V1, etc. Further, note that if a gas expands reversibly but adiabatically, then as for such a process Q reversible is equal to 0. Therefore, Ts is equal to 0. Entropy change during physical change, phase change. A change of phase occur in any one of the following case. First, when solid melt or conversely when a liquid freeze. When a liquid evaporate or conversely when a gas condense. Third, when one crystalline form changes into another. When the change of the phase, the temperature remain constant till the temperature of phase is completely. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called the latent heat. It is further termed as the latent heat of melting, latent heat of vaporization, etc., depending upon the nature of the process involved. In general, if del LH is a latent heat and T is a temperature at which the change of phase occurs, the entropy change accompanying the phase change will be given. Del S is equal to del LH by T. The entropy change del S is termed as the entropy of melting, entropy of vaporization, depending upon the nature of the process. For example, the entropy of melting or fusion is equal to delta SF is equal to delta H fusion by T fusion, where delta fusion H is the latent heat of fusion and TF is the melting temperature. Second is the entropy of vaporization. Del SV is equal to del vaporization H by TB, where del vapor H is the latent heat of vaporization and TB is the boiling temperature. It may be mentioned here the process like melting and evaporation involve the absorption of heat, which is taken as positive by convention of sign. Therefore, delta S for this process is positive. Example, these processes are accompanied by increase of entropy. On the other hand, the reverse process like freezing and condensation involve the evolution of heat, which is taken as a negative. Therefore, for this process, delta S is negative. For example, these processes are accompanied by decrease of entropy. It may be remembered that if the heat is measured in calorie, the unit of entropy changes are calorie per degree per mole. If it is measured in joule, the unit will be joule per degree per mole. Entropy change on mixing of an ideal gas. Suppose at constant temperature, N1 mole of the ideal gas 1 at the initial pressure P1 naught are mixed with the N2 mole of another ideal gas 2 which had initial pressure P naught 2. Suppose after mixing their partial pressure in the mixture of are P1 and P2 respectively. Now we know that at constant temperature the entropy change of an ideal gas when its pressure changes from P1 to Pf is given by del S is equal to R ln Pi by Pf moles inverse. Entropy change of the first gas when the pressure of N1 mole of gas changes from P1 naught to P1 is given by del S1 is equal to N1R ln Pi naught by P1. Similarly, entropy change of the second gas when the pressure of N2 mole of a gas changes from P2 naught to P2 is given by del S2 is equal to N2R ln P2 naught by P2. Equation second. Total entropy change on mixing the two gases will be delta S mixing is equal to N1R ln P1 naught by P1 plus N2R ln P2 not by P to consider equation third. If P is the total pressure of the mixture, example P is equal to P1 plus P2 and X1 and X2 are the mole fraction of gas first and second in the mixture, then by the Dalton's theory P1 is equal to X1 P plus X2, P2 is equal to X2P. Substituting these values in equation third, we get delta S of mixing is equal to N1R ln P1 naught by X1P plus N2R ln P2 upon X2P. Taking the simplest case in which the gas is taken at the some initial pressure and after mixing the volume of the mixture is same of sum of their initial volume. P is equal to V1 plus V2. The final pressure of the mixture will be nearly same as initial pressure of each gases. P1 naught is equal to P2 naught is equal to P. The equation fourth is simplified as delta S of mixing is equal to minus R N1 ln X1 plus N2 ln X2. Consider equation fifth. For the mixture of the number of an ideal gas, the equation fifth can be generalized to the form delta S of mixing is equal to minus R summation Ni ln Xi. To calculate the entropy change for 1 mole of the mixture, dividing equation fifth by N1 N2, we get delta S mixing is equal to minus R x1 ln x1 plus x2 ln x2, which can be generalized to the form delta S of mixing is equal to minus R summation xi n lxi. Consider equation 8. From the observation, we conclude that delta x is independent of other temperature or xi value always less than 1. Delta x will be taken as positive. The mixing of gases is accompanied by increase in entropy. Physical significance of the entropy measure of disorder. An examination of the various processes which are accompanied by a net increase of entropy show that they are associated with an increased randomness of distribution. For example, first the melting of a solid is accompanied by a net increase of entropy, and at the same time we know that the molecule, atom or ion in a solid have fixed position and they become free to move about in the molten state. This is expressed by saying that there is no disorder among the molecule, atom or ion in the solid, but the disorder set in which the solid change into liquid. In the other word, it is stated that the randomness has increased. Second, the vaporization of liquid is accompanied by a net increase of entropy, and at the same time the disorder of the randomness also increases, but the molecule of the vapor are more random than the molecule in liquid. Third is a heating a magnetized iron needle demagnetize it because the molecule of the magnetized iron needle, which were orientated in a particular fashion, loses the order on heating and become disordered. Randomness increases. 4. All spontaneous processes like the diffusion of gases, flow of heat from hot end to the cold end of an iron bar are accompanied by the net increase of entropy as well as an increase of randomness or disorder. For example, in the phenomena of diffusion, the two gases which are separately initially get mixed in a random manner. Similarly, in the flow of heat, the electron present on the hot end and having higher kinetic energy rush to the cold end, thereby making the distribution more random. And hence, it may be concluded that entropy is a measure of randomness or a disorder of the system. This concept may be further understood with the help of the following example. In a college, when all the classes are being held, all the students are sitting in their respective classes room and disorder is minimum. As soon as bell ring, the student of the different classes come out to go to other room and then mixed up. In the other word, disorder or randomness increases. Second, in a game of hockey or football, to start with all the player take up some definite position and thus are said to be in order. As soon as the game start, the players start running and thus they are said to have an increased randomness which increase further as the game catches more and more momentum. Thank you.